Namaste. My name is Dr. V Bindu Neeharika, Associate Professor in the Department of Mechanical Engineering in ANEX. Today I want to discuss you about the one of the optimization technique, that is geometric programming. Geometric programming is nothing but it is a solution. It gives a solution for non-linear programming, and this geometric programming was developed by the Defen, Peterson and Zenin in the year 1967. It is used to find the minimum of the objective function. So first we will see what will be the linear programming model problems. How will be the linear programming model problems? In the linear programming model, there will be an objective function with some constraints and consists of some variables. I will show how will be the objective function. 3x1 plus 4x2 plus 5x3. It will be in the maximization or minimization mode. That is, maximize z equal to 3x1 plus 4x2 plus 5x3, which will be your objective function. Which is subjected to some constraints such as 2x1 plus 3x2 less than or equal to 10, 3x2 plus x3 less than or equal to 15, x1 plus x2 plus x3 greater than or equal to 20. These three, 1, 2, 3. These three are considered as constraints. And which x1, x2, x3 are considered as decision variables or basic variables. Decision or basic variables. So this is about the one of the format for a linear programming problem. Now we will see that before going for a geometric programming problems, we will see polynomials. What is the polynomial? We will see the polynomial. Polynomial is nothing but where the function f of x equal to u1 plus u2 plus so on plus un, where that equal to sigma j equal to 1 to n uj. Okay, then what is uj? uj equal to cj I equal to 1 to n, I equal to 1 to small n, xi a ij, where cj is, where cj j equal to 1 to so on to n, which is called as a positive constant coefficient, and I equal to 1 to so on to the n, which is called as a positive design variables. Again, for xj, for aij, I equal to so on to n, I equal to 1 to so on to n, j equal to 1 to so on to n, which is called as an positive real exponents. Positive real exponents. Okay, so this function which consists of positive constant coefficients is coefficients, positive design variables and positive real exponents are called as a polynomial function. So for the unconstrained minimization problem, again this is about the polynomial. Now we'll see the unconstrained minimization problem, how it will be. Unconstrained minimization. In the geometric programming, we are having three models. We can solve the problems in three models. One is by minimization, constrained minimization problem. One is unconstrained minimization problem. And the one is complementary geometric program. These are the three models how we can solve the problem. So, how will be the first we will go for with an unconstrained minimization problem. This unconstrained minimization problem is nothing but it is a statement of unconstrained minimization problem where x equal to x1, x2, so on to xn, which minimizes f of x equal to f of x equal to sigma j equal to 1 to n ci which is nothing but this is called as a polynomial. Means here which consists of the positive constant coefficients, positive design variables and positive real exponents. So these three consists called as a polynomial. In this polynomial we have to solve the problems. Here we are going to solve with two different approaches. One is which is based on the differential calculus, and in the model we can solve which is based on the concepts of geometric inequality. Okay. Now we will discuss one of the unconstrained minimization problem. Here this is one of the unconstrained minimization problem. Here minimize f of x equal to 5x1 plus 20x2 plus 10x1 whole to the power of minus 1 and x2 whole to the power of minus 2, which should be solved by using the geometric programming. See, any of the problem, either the constraint or unconstrained, any of the problem which is of linear programming problem, we can solve in any of the methods, either in the geometric programming or linear programming method or integer programming method, dynamic, transportation or assignment, in any of the methods. But here now we are going to solve this problem by using the geometric programming method. So this is the problem given. First step, the solution, what is the first step is we have to find the f of x. Let x is x equal to, how many variables here? Here there are only two variables are given here, that is x1 and x2. There are two variables. So that's why we are taking x equal to only x1, x2. Why? Because here we had given only two variables. That's why we had taken two things. So for this one you have to find the number of functions in the objective function. In the objective function, how many functions is there? Capital N. Capital N is nothing but number of functions in the objective function. How many functions in the objective function? This is the one function, this is one function, this is one function. 1, 2, 3. 3 functions are given in the objective function. So number of functions in the objective function are 3. Capital N represents the number of functions in the objective function. Small n represent the variables, number of decision variables. What are the decision variables here? Here the decision variables here are x1 and x2. These two are the decision variables. So they are two decision variables in this problem. So the next step here in the geometric programming, you have to find the degree of difficulty, then the normality condition, then orthogonality condition. After finding these three things, then only you can get the objective function, which is nothing but the value of f of x. After getting the f of x, you will find the values for the variables such as x1 and x2. So now the next step is you have to find the degree of difficulty. The formula for degree of difficulty is degree of difficulty. Capital N minus small n minus 1. But in the problem it is given capital N is 3, small n is 2 and 1. This is the formula for degree of difficulty is capital N minus small n minus 1. Capital N is nothing but the number of functions in an objective function. Small n is the number of decision variables. So 3 minus 2 minus 1 equal to 0. So this problem is considered as a zero degree of difficulty problem. So it is called as, therefore it is zero degree difficulty problem. And the next step is the next step you have to find the normality condition. What is the formula for the normality condition? Next step is the normality condition. Normality condition formula is sigma j equal to 1 to n, that is delta j star equal to 1, where j equal to 1 to small n, where k equal to where k equal to 1 to so on to small n. Okay. Now, so you have to find what is in the problem. What is delta j? Here the problem is given here is 5x1 plus 20x2 plus 10x1 whole to the power of minus 1 and 20x2 whole to the power of minus 2. So here how many n value is 3. So what will be the normality condition here? J is 1, 2, 3 is the j. So then it will come j is delta 1 star plus delta 2 star plus delta 3 star equal to 1. This is one equation. You have to solve all the equations which you are getting in both the normality condition and orthogonality condition. In the normality condition, we got one equation, that is delta 1 star plus delta 2 star plus delta 3 star equal to 1. That is the one condition. Then coming to the next one is the orthogonality condition. Okay, orthogonality condition is nothing but sigma j equal to 1 to n a kj 1 to n a kj delta J star equal to 0. Delta J star equal to 0. Where K equal to as the same, just like a K equal to 1, 2, so on. Just same as that of normality condition. Now again you form the equations for this one. For this one we have to form the equations just like this. Where K equal to 1. Where K equal to 1. When K equal to 1, how the equation will come? A. Why? Because we are having 1, 1. A 1, 1 plus delta 1 star. Delta 1 star plus A 1, 2 delta 2 star plus A 1, 3 delta 3 star, which is equal to 0. Now coming to the when K equal to 2. Why? Because we know that n is 2 variables. Small n is 2 variables. That is K equal to 1 and K equal to. It is the first equation. 0 equal to 1 is the first equation. Okay, next one is K equal to 2. A, what you will get? A 2, 1 delta 1 star plus A 2, 2 delta 2 star plus A 2, 3 delta 3 star equal to 0, which will be your second equation. So now we have to find the delta variables, A variables. In the equation, in the formula, what is A11 is given x1 value, and how much is the x1 value? See, in the problem it is given that x1 value. What will be the, see, x1 is in the first function. How much is the x1 in the first function? 1. x2, there is no x2 there, so 0. So here the same way. So this one will be a 1 value. Why? Because x1 in the function is 1, first function, and x2 again in the same thing, x2 will be 0. See, in the problem it is given that here in the second function there is no x1 value. That's why I had given x2 as 0. When coming to here, then x1 value here is minus 1 is there. So here in the A13 value will be minus 1. In the same way, the function 5x1 is there. 5x1 plus 20x2. So here in the x2 is not there. So x2 is not there in the first function, so it will be 0. Here x2 is there, so this will be 1. Here x2 is there, it will be minus 1. So what is the equations you got here? Delta 1 star minus delta 3 star equal to 0. This is a one equation. And another one is delta 2 star minus delta 3 star. This will be the second equation. This will be the third equation. And the first equation we have already find in the normality condition, that is delta 1 star plus delta 2 star plus delta 3 star equal to 1. This is the equation 1 which we have already got in the normality condition. So by solving all these three equations, we got delta values as, by solving all these equations, we got delta 1 star equal to 1 by 3, delta 2 star equal to 1 by 3, and delta 3 star equal to 1 by 3. By solving all these equations, by solving equation 1, 2 and 3, we got delta 1 star equal to 1 by 3, Delta 2 star equal to 1 by 3 and delta 3 star equal to 1 by 3. Now you have to find the objective function. What is the objective function? Objective function, it is also given as like this. To find the objective function. To find the objective function f of f star equal to so again we can write this one in which format? Delta 1 star by having J capital N is how much? 3. So we can write this one as C1 by delta 1 star whole to the power of delta 1 star into C2 delta 2 star whole to the power of delta 2 star into C3 delta 3 star whole to the power of delta 3 star. So now solve this one. What is the C1 value? C1 value is nothing but in the problem what is the coefficient? See, I'll show you the C1 value. See, this will be your C1 value. 5 will be your C1 value. Where the coefficient of the function, first function will be your C1 value. Coefficient of second function will be the C2 value. Coefficient of third function will be your C3 value. So then you will get it as C1 will be your 5. Then what is your delta 1 star? Delta 1 star we had already got it as 1 by 3 whole to the power of 1 by 3. Then C2 value is 20 and delta 2 star value is 1 by 3. Then whole to the power of 1 by 3. And third C3 value is 10. 10 by 1 by 3 whole to the power of 1 by 3. So by solving this, we get the value as 29.98 or 30. This is your actual function, objective function. You got the objective optimal solution. This is your optimal solution. You got your optimal solution. Now what do you have to find? You have to find the design variables or decision variables. So now we will find the decision variables. To find the decision variables, to find the decision or design variables, the formula given as Uj star by f star. F star is nothing but the optimal value what we have got now, that is 30. So that is equal to delta j star. That equal to j is how much? 1 to small n, capital N. J equal to 1, 1, 2, so on to capital N. Capital N is nothing but 3. So then what? You want to use J star equal to, you got the values of F and delta J. Uj star equal to F star into delta J star. F star is how much? 30, what you got it. And delta star is 1 by 3. Okay, delta 1 star is 1 by 3. Then U1 star is, U1 how much? U1 is the first objective function, that is 5x1. Then you got how much you got? x1 how much you got? By solving this, you got x1 value as 2. Okay. Now you got variable of 1. Now we will find the next variable. That is u2 equal to f star into delta 2 star. u2 formula, what is the formula for 20x2? Function of second function in the problem. 10x2 equal to 30 into 1 by 3. 10. x2 equal to how much? 1 by 2. So here the solution of the problem is f star equal to 30, x1 equal to 2, x2 equal to 1 by 2. This is the solution of your problem. You have to find the value, optimal solution, optimal value, then the design variables x1, x2. This is the problem. This is the solution for your unconstrained minimization problem by using the geometrical programming method. Now we will see how to solve the constraint minimization problem by using the geometric programming problem. So here the problem is given as minimize f of x equal to x to the power of minus 1, x to the power of minus 2 and x3 to the power of minus 3, which is subjected to a constraint 1, which is x1 whole cube plus x2 whole square plus x3 is less than or equal to 1. This here we have taken only one constraint. So xi is greater than or equal to 0, I equal to 1, 2, 3. Now we will solve this problem. First we will state the optimization problem statement as follows. The optimization problem can be stated as f of x equal to, here how many variables are there? Here 3 variables are there, that is x1, x2, x3. So there are 3 variables. So x is given as x1, x2, x3 so as to minimize n equal to n0 plus n1. Why? Because n is, as we had already discussed in the earlier class, that n is nothing but number of functions in an objective function. Here this is objective function is there. In this problem objective function is there, constraint is also there. So n0 will be considered as an objective function and n1 is considered as constraint 1. If there are more constraints, then we consider as, if there is a constraint 2, then we consider as n2. If there is a constraint 3, we consider as n3. So how many functions in the objective function? Only one function. This is the only function which is there in the objective function. So 1 plus how many functions in the constraint? 1, 2, 3. 3 functions are there. So we consider as 3. So n is equal to 4. Now coming to the variables. How many variables are there? x1, x2, x3. Small n, as we had discussed, is nothing but a number of relation variables or design variables. Here x1, x2, x3 are 3 design variables. So capital N is 4 and small n is 3. So now we have to find the degree of difficulty. Degree of difficulty formula is capital N minus small n minus 1, that equal to 4 minus 3 minus 1, that equal to 0. So again it is a 0 degree difficulty problem. Therefore it is 0 degree difficulty problem. So first step has been completed and the next step is we have to find the normality condition. Normality condition, What is the normality condition? In the normality conditions, how many functions are there? Here the normality condition is normality condition as given as lambda 0 1 equal to 1. Why? Because in the objective function there is only single function. That's why we consider normality condition as lambda 0 1 equal to 1. This is the step 2. This will be our first equation. Coming to the next is orthogonality condition. Orthogonality condition. How many variables here for the orthogonality condition? There are 3 variables. So we'll get n equal to 1, that is a01 plus lambda a lambda a01 a0 lambda 1 plus here there is a a011 a012 lambda 02. How many equations? This is for constraints. Here this is for objective function and this is for constraint. Constraint we are having a1. So, for a0 plus a lambda 1. For constraints, what is a111? A111, a1, a11 plus a1 1 2 lambda 12 plus a113 plus into lambda 13. This is for equal to 0. This is first one. So next n equal to 2. So n equal to 2 is a012 lambda 01 plus next one is a121 lambda 112 lambda 11 plus a122 lambda 12 plus a123 lambda 13 equal to 0. Then n equal to 3, that equal to a013 lambda 01 plus a131 lambda 11 plus a132 lambda 12 plus a133 lambda 13 equal to 0. So here, what you will get it? Lambda 11 in the first equation we had given as -1. And lambda 11 it has given as a31 is 3 it is given. And for this one, these two are zeros. X1 value, see x1 value in the first equation. The first equation x1 is -1 and this one is 3. So that's why we had taken like that. Then coming to the x2 value -2. Here it is -2 and 0, 2, 0. Then coming to here x3 value -2, 0, 0, 0, 0, 1. So now the equations will get it as minus lambda 01 plus 3 lambda 11 equal to 0 is your second equation, and -2 lambda 01 plus 2 lambda third equation. Then minus 2 lambda 0 1 plus lambda 1 3 equal to 0 is equation 4. By solving all the 4 equations, we will get solving all 4 equations. We get lambda 0 1 equal to 1, lambda 1 1 equal to 1 by 3, lambda 1 2 equal to 1, lambda 1 3 equal to 1, 1 3 equal to 2. So then what are the C values here? From the table, from the problem we had got C1 equal to 1, C01 equal to 1, C02 equal to 1, C03 is also equal to 1. So you can write C1 here as, so C01 equal to 1, C11 is also 1, C12 equal to 1, C13 is equal to 1. So now find the function. Or f star equal to C01 by lambda 01 into lambda 01 whole to the power of lambda 01. Then same way for the next one, C11 by lambda 11 plus lambda 12 plus lambda 13. In the same way you will get for C12 by lambda 12 into lambda 11 plus lambda 12 plus lambda 13 whole to the power of lambda 11. Here whole to the power of lambda 12 into C13 by lambda 13 into lambda 11 plus lambda 12 plus lambda 13 whole to the power of lambda 13. This is the formula for the constraint optimization problem. So now we will solve this. We got the C1 value as 1, lambda 01 value as 1 into 1 whole to the power of 1. Then C11 value as 1 and lambda 11 value as 1 by 3. So by adding all these 3, that is 1 by 3 plus 1 plus 2, how much you are getting? 10 by 3 into 10 by 3 whole to the power of 1 by 3 into lambda C12 is 1 by, how much is lambda 1 by 2? Lambda 1 by 2 is given as 1, again 10 by 3 whole to the power of 1 and C1 1 by 3 is 1 by CE 1 by 3 is 1, 10 by 3 whole to the power of 1. So the solution for this, by solving this one, the solution you got here is 19.9 or 20. So the optimal solution you got here is the 20. Now you have to find the design variables for this one. You got the f value. Now to find the design variables. Same formula, design variables also you have to find like this. Lambda 01 equal to C01 by f star into the function is given as what is the objective function x, x1, x2 square into x3 cube, x2 square. So this you have to find it. Lambda 01 is given as 1 here and C01 is also 1 and f star is 20 into 1 by x1, x2 square Here for this one, lambda 11 by lambda 11 plus lambda 12 plus lambda 13 equal to C11 into 1 by C11 into x into x1 x3. Why? Because this is for constraints. That's why the formula is like this. Then lambda 11 is 1 by 3 by 10 by 3 equal to 1 into x1 whole cube. This is one thing. Then you got x1, by solving this one you got x1 equal to 0.464. This is the x1. Now we are coming for the next one. So find the next equation is lambda 12 by lambda 11 plus lambda 12 plus lambda 13 equal to, the next equation has given us C12 into x2 whole square. So now we will find the x2, that is lambda 12 is 1 by 10 by 3, that equal to C12 is 1 into x2 square. By solving this you got x2 as 0.547. Okay, is it clear? Now coming, we got the x1 value and x2 value. Now we will solve the x3 value. x1 by 3 into lambda 11 plus lambda 12 plus lambda 13 is C13 into, and the constant is given as x3. So that is lambda 13 we got as 2 by 10 by 3 equal to 1 into x3. So by solving this we got x3 as 0.6. So these are the three design variables. Design variables you got as x1 as 0.464 and x2 as 0.547 and x3 as 0.46 by solving the equations. So and the f function, the optimal function, what you got x star equal to 20. This is your optimal value. So in this way you are going to solve the problem, linear programming problem by using geometrical programming problems. So we can solve this linear programming in any of the methods, but by solving the geometric programming problem, first of all you have to find the degree of difficulty, then orthogonality condition, then normality condition. After getting all these things, you get to the three certain equations. By solving these equations, you got the lambda values. By getting the lambda values, you will find the objective function or optimal function. This is the objective or optimal function for a constraint problem. So this is the solution for that problem. After that, you find the decision variables.